Thank you very much again for inviting me today. I hope my sound is clear. Today I will be talking a little bit about some of the vision AI and science engineering application. Not only what we have been working on the last 2 years or so, but also gives a perspective a little bit as we move forward into how this might impact or might help shape a little bit the development in AI-based science and engineering to Fugaku NEXT and beyond. My name is Mohamed Wahib, and I work for RIKEN CCS Center for Computational Science. I have to acknowledge first that a lot of the work in this slides are with collaborators inside RIKEN, outside RIKEN, and many organizations in Japan and also outside Japan. Number one, why is AI relevant to science and engineering? Just a casual reminder. A good example is that, back in history, we can look in science and engineering application that astronomers observe regular predictable motion of celestial bodies, like other planets or moons or so on. And they always had a question, what governed the motion? And then came someone, Isaac Newton in this case, and also people before him who he built his work upon, that work backward from observation, that there's some universal mass that acts. So effectively, in this case, the science was reverse engineering nature, right? By mostly observing the pattern. So observing pattern or pattern, acknowledging the pattern to work your way backward, to nature is a very important thing here. Effectively, machine learning is very good in finding a pattern. This is exactly what machine learning is. A good example is if you use ChatGPT or if you use any similar chatbot, when you are asking a model, for example, you start with a prompt, the sky is, what the model is doing is trying to detect what is likely to be the pattern, basically. If the sky is your prompt, what is likely to be the next word to continue the sentence. So it's predicting from a pattern, one token at a time or one word at a time. So machine learning is very good at finding pattern. So in AI and science, the main premise is that AI is a pattern recognition machine, or very capable in pattern recognition. And how can we use that to improve our capability to understand nature? And this is where practically the modern use of AI, or machine learning to be specific, data-driven methods, can help in understanding nature. And if you look, for example, in recent breakthroughs in AI-based science, bring 2 examples, which was AlphaFold, and another one, which is GraphCast, which is one of the first papers that showed practical capability for weather prediction based in AI. If you look at both, and again, very 2 widely cited papers, if you look at them, even in their title, right, there's prediction, right? They're basically trying to use the model to predict, improve protein structure, and here the forecasting, which is again prediction. So basically, what's happening in AI science is trying to use the capability of AI in finding pattern. So I will narrow down a little bit here in the rest of the presentation and talk about the use of AI in particular for spatial and spatio-temporal data. Data in science come in all types and all shapes in very wide range of domains. But again, for the reminder here, I will be focusing only on spatial and spatio-temporal. Why spatial and spatio-temporal, you would ask? Because actually complex spatio-temporal data is very common across very wide ranges of science and engineering fields, from fluid dynamics to climate and weather, remote sensing, beam lines, industrial inspection, X-ray, electron microscopy, and more actually areas that are not on the slide. Multidimensional imaging are ubiquitous, and you find them across a lot of science engineering, and they vary a lot. This is not an exhaustive list. This is just a few examples that give some numbers on the nature of images that you would see in weather, climate, satellite imaging, microscopic, electron microscopes, videos, X-ray, CT, MRI. And then you can see they vary widely in resolutions, right? From 100K to 100K pixels, which is very high resolution microscopic, to less so. And they also can be 3-dimensional or 2-dimensional. They vary a lot in how many tokens, and I will explain later on what token means. But token you can think as the unit of information that you extract from an image to use with AI. They vary also a lot in dataset sizes, from tens of petabytes, if you look at the raw data, all the way down to tens of terabytes.
I want to understand the unit. What's S in the resolution? S.
Hundreds. Sorry, so it's as if it's order of hundreds. Yes, hundreds
just counting numbers.
Yeah, just counting. Yes. So it's giving orders rather than exact numbers. So tens of channels and tens, hundreds, like 300, 400, 500 cubic. Yes.
And K is the kilo?
K is kilo, yes.
Okay.
So to interpret this, like 100K square means 100,000 by 100,000 image, two-dimensional. In weather and climate, you can think of a discretized mesh as hundreds by hundreds in size and has tens of channels. If you go for ERA5, the analyzed data set, and the channel here are basically prognostic physics, not the typical channels of colors like RGB. Okay, same here. When I say 100Ks, like this is like hundreds of thousands of tokens per sample. And I'll explain this again more in detail. Dataset sizes also vary in size. Thank you for the question, sir. It's a very good question, actually. I maybe should clarify this more in the future. Dataset sizes can vary by orders of magnitude from tens of terabytes to tens of petabytes, so 3 orders of magnitude. Also, the dimensions and channels vary a lot. It can be spatial and temporal, it can be 2D, it can be more than that. The number of channels can be very high, like N channels. It can be much lower. Again, this is a table to show some example of the areas to show how much diversity we have in spatio-temporal data. So before I continue much toward that, of course, handling spatio-temporal data doesn't need to necessarily be done with transformers. There's so many AI models that are very capable. I will, however, focus a lot from now on Vision Transformer in specific, and I'll explain later on why Vision Transformer, not because it has a particular advantage. Sometimes very well-crafted models can outperform transformers. But the thing about transformer or Vision Transformer, that it has the capability to learn with huge amounts of data because it has a receptive field of entire images. And I will explain what that exactly means. So a Vision Transformer, first a transformer, before we move to vision, so explaining what a transformer, because they start from languages. So they did start from modeling a language, right? Trying to find words and find the meanings, right? A very simple example is, say, if you have few words in the English language, like bird, horse, virus, plane, you can choose one single number to represent how the words are semantically close or far from each other. So a bird, a horse, or human, you can assign them just one number, 10. A plane and car and train, give them 100. And here, close or far in meaning, is it a living thing or not? So if the words represent some living thing, they are closer to each other. If they're not, they're far. You can easily recognize that the problem with this is that 2 words can be close semantically in one way, but also different in another way. So if I, instead of using just one number, like this, dimension 1, I make it 2-dimensional, and I make this axis fly. Can this object fly, or can this noun fly? And this is living thing. Then you start to see a very different shape. So maybe bird and plane, as you can see them here on top. I maybe should use a laser pointer. So bird and plane, as you can see, they have a closely by number because both they can fly. But in another word, if you're looking at the attribute of are they a living thing or not, you can see they're very far apart. Here you can see that each word can be represented by a vector, basically. This is a vector space. In this example, it happens to be of dimension 2 only, right? This is how, in transformers, people are representing the words in a language. And what a transformer does, or what exactly self-attention does, which is the main component driving transformer, is trying to find like a semantic regularity. So they start in this space by saying, let's say, for simplicity, I'm showing only 2 dimensions. In reality, it's much more than that. But for simplicity, let's say they try randomly from different places. But what you do iteratively, and let's say also you don't even know what close in meaning is. So you don't have to dictate and say, I want this attribute or this dimension to mean fly and this to mean living thing, but you just make it a latent variable that is something can be inferred but not observed or defined. And you iteratively, in training, change the position of each word in that vector space. Again, repeatedly training step 1, training step 2, training step 3, until the words are spread out such that, again, it reflects if the words are semantically close or far from each other, right? And this is what more or less happening with transformer. This is a job of the transformer, or the self-attention to be specific, right? That was transformer as when your input is words like this, right? This is where it started from. So basically, to build this, right, you need to go through something like this. It's quadratic. So you're trying to find the relation between each word in a sentence, right, and each word, each of the other words in the same sentence. That's why this looks like a quadratic. So if your sentence was like this, it looks small outside and so on. The cost for memory and also compute becomes quadratic because you need to do a pairwise relation between each two words, just like you did here. For each one of those words, to find its place in this space, you have to compute how it's close to each one of those, right? You can think of it, if you're coming from the space of computational science, as if it's like an n-body problem where you do it in a naive way, where the cost is n square. You compute the gravity forces to every single other body. But that was for text. Remember, the topic of this presentation is about vision and spatial and spatio-temporal data. Well, people realized if the model, the transformer encoder, can take in words and words become what they call tokens, you can simply tokenize anything. So what happened is some people proposed take an image like this on the right side, animated figure you see here. And it's from that paper written down below, the first paper that proposed vision transformers, and split it into patches. So each image becomes a set of patches. A patch is some pixels, like 16 by 16 or 32 by 32, and take each one of those and then extract from each patch what they call embedding or features, right? Basically, the vector numbers you see here. Just like each word was represented by a vector of numbers, you can do the same actually with an image. You can train a very tiny small model that sits here, right? This linear projection of flattened patches, right? This is learnable to extract a numerical vector representation or embeddings of each patch of those. And then suddenly it's the same as language. Suddenly your input is a sequence of tokens. It's just that these tokens came from an image rather than each token becoming a word. And actually, this is pretty much generalizable. So whenever you see a transformer using with any data type or modality, what people try to do is to transform the input. It could be a continuous signal that they discretized, and then they feed it. It could be an image, it could be a video, it could be text, etc., right? So you can tokenize anything, right? So a little bit before I go more in detail on the use of that. So on vision transformer and something called inductive bias, okay? First, we know that neural network has something called the universal law of approximation, meaning that if you have any continuous function, by having at least one hidden layer and sufficiently wide enough, you can map any function to any function, which is a very strong capability. It means if you want to map between two things and you don't know the function, you cannot know it, which is mostly the case in complex problems in scientific computing. If you have an inverse problem, for instance, it can at least learn the mapping. You can give it an input and it can tell you the output without actually knowing the function itself, which is called the universal law of approximation, right? That being said, this gives you a bound on approximation error. So this guarantees you that there is a bound on how much error happens when I map from this to this. But there are other types of error. That is, there's something called generalization error. That is, if a network sees samples to train on, to generalize to that hasn't seen before, this introduces other type of error. Then there's something called the optimizer error. That is, to find even the optimal weights for this, you don't find the you don't find the optimal solution because this is a high dimensional space, and it's a combinatorial problem, and you get exponential cost to do that. There's a very high number of model parameters. So, for example, you would hear a model is 70 billion parameter, means this is an optimization problem for 70 billion degrees of freedom, right? So this is an optimizer. Usually choose an approximator or simple optimizer that finds some good local minima, like gradient descent or so, but doesn't go beyond. So that means, to summarize, in practice, why are we not using just simple network that looks like this, which is called fully connected? Because in practice, we know there are other sources of error. Hence, we need some like clever design of the model that uses the same underlying way to train and learn and so on, but can be much more better in trying to learn, right? And this is what Vision Transformer was born from, right? First, there's something called inductive bias. Inductive bias in the space of machine learning or neural network, to be specific, is that you make assumptions that a learning algorithm uses to predict unseen data. Okay, so to give a clear example, let's take a step back. We said that a neural network is just basically a sophisticated pattern recognition machine, right? Then the best way to have inductive bias, that in other words, the design of the model reflects the type of pattern you want to know, right? That means you add network elements. You don't just go with this naive, fully connected structure. You add network elements to work better with the pattern in the data. And this is something general, not specific to vision or so on. So for example, if you happen to know that your data is usually spatially local, for example, images, like if you happen that a cat, for example, usually the features in a cat's face are located spatially in a very local part of an image. They're not scattered around. So you need an effective way to capture patterns that are spatially local to each other, or there's high locality. And this is where convolutional neural network was born, because they tend to look in the very close proximity locally to extract features. If you, for example, happen to work with data where the pattern you're trying to catch or recognize or model is temporal, then you can use, there's a design that's called recurrent neural network that is much more, carefully designed to try to capture and is more effective in capturing this pattern. If, for example, relationships are structural, so there's dependency between different objects, then a graph neural network makes sense. If it's pairwise pattern, that is, elements of your input, like which was language, if you remember, had sequence of tokens, and you want to feed pairwise patterns, the transformer, and to be specific, self-attention is ideal. You will imagine for a long time for vision, people use this one on the left because we know that spatial local patterns are more effective. And then people figure out, well, the good upside of using transformer is that the receptive field becomes the entire image, right? That is, you are not local anymore, but this is maybe you would imagine actually as a downside, not an upside, right? Because you're learning a lot of things. But the upside is the model can absorb a lot of training data, right? So to shift here, so for inductive bias point of view, you might imagine, okay, vision transformer doesn't make any sense or much sense, let's say, versus a convolutional network, which makes a little bit of sense that you're looking for spatially local patterns. Because the receptive field is the entire image. That means each piece of the image attends to all other pieces of the image, which again might not make sense. However, the positive of that, or the reason you might want to do that despite not having a good inductive bias, not good design for what you're trying, the pattern you're trying to learn, is that the model learns everything because it can ingest massive data sets, and I emphasize ingesting massive data sets. But funnily enough is that also this is a negative, because the model, because it learns everything, it's so expensive because you're paying a quadratic cost for compute and for memory, and you're also finding irrelevant patterns sometimes. And I guess the reality is you sit in between these positives and negatives to find something that works. So as we said, there are particular vision transformer issues versus text transformer issues. Number one, transformer, as we said, consume sequence of tokens, which is more fit to the nature of text. Text tokens, you can imagine that they're atomically semantically distinct and rich in information. So what does this sentence mean? It basically means in text, each word can have a lot of effect on understanding. And this is pretty easy. I can easily give examples of sentences where if I just remove one word from a sentence, it makes the meaning ambiguous or destroys the meaning, right? In visual tokens, they're geometrically related and sparse in semantics, meaning that you can easily take an image, remove a pixel or change its value, and it will not take away from what the image is representing. So this is a very big distinctive, distinction between vision or visual tokens versus text tokens, right? But on the other hand, also for vision, the loss of hierarchy information becomes more pronounced, right? There's no notion of hierarchy in text. Text is just flat sequence of like words, right? There's no hierarchy of information, unlike images. And hierarchy, to simplify, is like zooming in and out. If you have a high resolution image, the more you zoom in, the more details you see. And this is what I mean by spatial hierarchy. So the information is spatially hierarchical, unlike text. So those are two main distinctions, again, that distinguish text tokens from vision, and which, in my opinion, drives a lot of the differences in design between transformers for vision tasks versus transformers for text. Of course, there's commonalities. Of course, they both are using the underlying same neural network architecture, but there are also differences. So those are some of the challenges that are maybe, I would say, distinguish a little bit vision transformer from just transformer for text, long sequence, shifting bottleneck, tokenization, and different parallelism. And as the reminder of this talk, I will basically mention each one, but when I mention it, I mention like work that we try to do that solves the real world problem and solve it through also addressing the challenge at the same time. So it shows that, addressing the challenge is not happening, in some, void that detached from real world problem. It's the other way around. We start from a real world problem and work our way backward to solve the problem. So, and this is, was helpful in many aspects in microscopic pathology, X-ray, computed tomography, and also wizard prediction. First, long sequence. What does long sequence mean? Long sequence, remember, the sequence is the input, tokens, basically, right? Remember we said you take an image, you split it into patches, say 16 by 16 pixels, and feed it to an LLM. There was a study that was, I think, very important that showed that if these patches or these blocks that you split the image into become very big, you start to have not a very good quality of representation. So say you want to do segmentation, that is defining objects in an image, which is a very fundamental operation, right? That can be used a lot. For example, if you have microscopic images and you want to identify cells, something like that. For ground truths, this is the ground truth of this figure from that paper. And you saw if your patch size is big, then the model is not able to do very effective segmentation. As you see here, the area is a big blob having 2 people. And as you reduce the patch size, 16 by 16 to 8 by 8, you start more and more to get much higher quality segmentation, in comparison to ground truths. Now, the downside for that is when this patch size is small, that means you're dividing your image into smaller patches or tiles. That means you have much more longer sequence. And this means that your input is very long. So for instance, if you have a 4K cube 3D image, X-ray CT image, for instance, and you divide it into tiles of 4 by 4 by 4. So I guess this is missing the 4 because this is 3D. That means for every single image, you have 1 million tokens, right? And remember that the cost that you're computing pairwise relation between each pair of token. So the actual compute cost and memory requirement is quadratic. So it means this is 1 billion, not million actually. This is 1 billion square, which is basically intractable, right? It's a big challenge, like we mentioned, that the compute and memory cost becomes here to compute the attention score, how much each token should attend or focus on other tokens. It's quadratic, so this is expensive. In the future, there has been a lot of ways people addressing that. This is one of the most rich areas of research. Some approaches used are well known in production, some are in research. I can even skip that, and some of them are compatible with each other, so you can use them in combination with each other. Some of them are not. I guess this is the part where I can skip because it gives a long overview of long sequence. But I'll jump here to one approach we used, basically in our case. And for a real world problem, which is, pancreatic cancer detection, those are what they call WSI, whole slide image. Think of it that it's a tissue sample. You get an image from a microscope, and it can be up to 100,000 pixels. That's very high resolution. Compared to, say, a photo you take on your phone, which is a few hundred by a few hundred, or at most 1,000 by 1,000. Used widely in pathology to study tissue and study cancer cells and so on. And there's challenges year after year trying to study that. So one thing we noted is, well, as we said, this is a very blunt tool that's doing pairwise, relation. So in traditional patching or traditional tiling to give the input to the transformer, no matter what the transformer is, there's so many varieties of transformer, but all of this is just to take the input, prepare it in a way to be tokens and give it as, it's like pre-processing or done at the input preparation or tokenization stage before you hit the transformer below. So that effort you have to do anyway. Traditional, which is on the left in black, you take each block in this image like that, and you flatten them into patches. So you take each row and put row after row after row. This becomes your input, right? But if you look at this, it's very obvious by eye that all this white space is useless, right? We know that whatever you want to recognize in this image, in this tissue, the tissue is, this, pink reddish color here. Anything in white is useless. So why am I giving all that to the model? Which is a very, very, clear, intuitive thing. And for that, we kind of propose, well, one way, other than the other ways I mentioned, there's so many ways you can try to make the cost here less. But this is one alternative way, which is takes cue from, takes a hint from what people have done in HPC for a long time with adaptive mesh refinement, in which people in HPC recognize if you have a solver over a mesh, if it's uniform, if you want to reduce the cost, you can just focus on the areas where you have more details and then refine more. And then hence adaptive mesh refinement have been used since 1990s or maybe even late 80s, right? And there are established methodologies for that in HPC, but not in this space. So we copied a little bit idea and said, maybe have coarse grain identification of the details. For example, here's these edges. Basically represent it. This is a 2D image, so it's a quad tree. And if you're familiar with AMR, it sounds like very classical AMR. You have a quad tree. If you visit all the leaves from the left to the right, it gives you a Z-order curve, which gives high locality. And then instead of all these black points becoming blocks, those of course are different sizes now because it's adaptive, but you can always downscale, so you maintain that each patch has the same size. But this scattered sparse pattern, from which also you know where your neighbors are due to the Z-order curve, is basically much more less than this. While this was 400 patches, this is 4,000, this is 400 or something. So you would say, well, you save 10x, much more like 100x, because keep in mind, once the patches or the input goes to the transformer, the internal cost is quadratic. And that led to like very decent improvement. This is the state of the art. If you look at the lower row, this is a 64K by 64K image. So it's very zoomed in at 0.006% zooming in. This was the state of the art. Basically, you cannot recognize anything of value. Ground truth is here, so you want to recognize the distribution of different colors of the tissue, because this is an indicator of whether the cell is cancerous or not. But with adaptive patching, you start to get somewhat good results, 77% accuracy, but it's much higher than what you already have with ground truth. And that also gives you humongous speed up, like up to 10x or so. So this is one example. I think I can skip here for sake of time. Another example, which because of that approach, also other than pathology whole slide images, we're able to use Vision Transformer to do geometry correction for real-time reconstruction of X-ray CT. And that's an example of a bumblebee, like a small, type of bee, where you're able to construct a very high resolution. That's because, again, you can handle long sequence. Another challenge, which is, shifting the bottleneck, right? That's specific to Vision Transformer and not text, is that even if you use these approaches to make the cost much less, there's something called a decoder. That is usually the image encoder here. This is the transformer part. But if you want, for example, recognize objects, you need something called a decoder. The mask is basically the segmentation result. And you need to use some object here to do that, which is CNN convolutional network mask decoder, which, to make it short for you, a lot of memory is required here outside even the transformer. So even if you make this part efficient, other parts become the bottleneck, and hence it becomes a shifted bottleneck. And to that end, we have proposed a way in which there's different views of the input image that are fed through different hierarchical trees, and then the model itself can learn this, which is very, again, helpful in medical imaging. This will work under review, and I think it looks like it's going towards an accept. And it's quite helpful in 2D and also 3D, and gives you much better, improvement, especially for high resolution. You can improve accuracy by 5%. 5% is a very huge jump in accuracy in these kind of problems. But I guess also one interesting thing is if you think more forward, And this is more forward-looking. We have not, started yet working on that, but I guess it fits the context of FugakuNEXT. We're looking into the future. Is in all these efforts, we're still, in a way, as humans, designing ways to tell the model where to look. But can we teach the vision transformer where to look? That is, instead of telling the model where to look, can we take an image, create a hierarchical differentiable tree, right? It has to be differentiable so that it becomes learnable, so you can use, automatic differentiation approach and the chain rule to be able to learn that tree. So you basically learn the spread of hierarchy. So the model itself takes samples. You extract a tree from it, something called the Gumbel tree, and you give that to the model, meaning that the spatial hierarchy becomes learnable itself. So that in the future, when I give an image to the model, it doesn't just ingest all the input in a naive way. No, it learns where to look at, right? Kind of like, if I give you a video and I tell you to identify an object and you start to focus on it so much, you immediately recognize this is an object. You don't look at other things and just keep looking at one thing only. So this is, I guess, where probably models or vision transformers will be next, where we can teach them not just, to recognize object in an image or classify, but also to begin with where to look in an image. And we kind of applied this a little bit in an application with Institute Science Tokyo researchers, in which they wanted to recover scenes from Wi-Fi signal, something called CSI, which comes in radio signals. That is, it's radio signal from spread out Wi-Fi devices. And the question would be if there's occlusion, that means if some object is hidden, can you use this signal to combine it as a multimodal way with an image to recover back. And I think this was fairly successful. Another one is called tokenization, another challenge, and I guess here where I have to move a little faster because of time. Tokenization, if you remember, is taking an image and dividing it into small tokens or patches or tiles. In spatial-temporal data, not in spatial data, it's easy. If you have an image, split it into tiles, 2D, 3D image, whatever dimension, doesn't matter. But what happens if you have time also? How do you split time? How do you tile time? Right? And by the way, again, HPC community has been doing that for a long time because there's something in HPC when you want to have more cache-friendly, code, something called tiling of your loops, to fit in cache, which is done commonly if you have memory-bound stencil-like operations. And there's also temporal blocking. So these are common techniques, but here you see them in a very different context. That is, how can I split? I take frames of a video, I split them this way, do I take all the frames, do I take a subset of frames, do I do radial? And this is a huge, area where people are looking at way to tokenize, which is very distinctive from, again, text, where text is just, hey, it's easy, take the words in a sentence and split them, it becomes, tokens. I will not go through here, but again, there's a lot of activity in that area, not just us and others are looking into how to split time in an effective way such that the vision transformers can learn in a much more effective way. You can skip this. Also, different parallelism, right? So for instance, if you happen to have a weather climate simulation, and this is a work I'm collaborating with Oak Ridge, it's a Gordon Bell climate finalist, in which they are feeding, the model as an image. Generally speaking, you can just imagine that you take a discretized mesh in this case, and just feed it as an input. It looks like an image, and each one of those, prognostic physics, humidity, wind speed, temperature, and so on, it basically becomes as if it's a channel, right? So it looks like a 3D image because the atmosphere is 3D, and the channels of that image are not colors; they're physics values. And what you realize here is that you basically run into an issue where tokenization itself, right, becomes an issue because you have so many channels versus classical images, which is just red, green, and blue. Those are basically maybe hundreds, a couple of hundreds. If you focus on the important ones, there are likely a few dozen or so, but that's a very high number of channels. So that means you need to scale them, these models in a very different way because now you're using a very different type of parallelism in which you're compressing the inputs and you condition the prediction on reduced uncertainty to do that, right? To in the end, predict in the future, in the next time step, the physics, values you care about. And again, along that line, which is another work that should appear in SC this year, is distributed tokenization, in which we realized, well, the channels or the tokens, if you assume each channel here is some physics prognostic variable, other than the typical classical ways where people take a transformer and parallelize it, and this is a whole big, field of study. There's many ways you can parallelize this, as a pipeline parallelism, tensor parallelism, data parallelism, context parallelism, etc. There's like 4 or 5 ways and combinations of them. This is what we call channel parallelism, in which we actually do the channel parallelism. This is specific to this type of problem because we have so many channels that we can, take it as an opportunity to do channel parallelism. But then we have to figure out a way where we do aggregation of the channel in a more cost-effective way. Final one is multimodality. I guess probably you heard a lot the word multi-agent, and multimodality is becoming a very big buzzword. A lot of people working in that area. And you can imagine that if you have different scientific data that represent different aspects of the same phenomena, in this case, let's say you're studying animal behavior or so. So you have neural activity, you have image, you have calcium images, you have genotype data, phenotype data, etc. You want your model to tap into this data, but you want different agents or different models, each model specializing in one modality, interacting together to be able to extract the data from one model. And to that end, again, this is a very complex problem. To that end, you need some system by which you're able to push all this data coming from scientific instruments. It could be even passively, that you set the data being collected to be in a passive way, just transferred all the time or streamed in, or you could be doing it in an active way where you self-control. This would sit on a bucket, and you need a system software layer here that manages how all these data modalities and the agentic access can be managed, so that you can, as a scientist, run your scientific inquiry. How much am I on time now, Inesa? Should I stop or keep going?
Okay, please keep going.
Okay. So, but I guess also for sake of everybody's time, I will make the next few slides also a little bit. This is just a project we're working on with RIKEN Spring-8, Oak Ridge National Lab on R-CCS, which is trying to actually see, okay, how can we do, if there's infrastructure inspection. Infrastructure means roads and highway networks and bridges and so on, which is so expensive. Traditional is manual or uses mechanical engineering, right? Or some laser imaging of the surface of the objects, but you can't see subsurface. And the question was, can we transfer from this mechanical traditional engineering approach to informatics, purely informatic approach, in which we can rely on X-ray CT imaging and more advanced 3D image analysis? This is the main challenge, basically. This is important because there's so many roads. Like, for example, in Japan, you have about 130,000 kilometers of highways, and there's even like small prefectural roads and so on. Inspecting that is just too much. It takes so much effort and so on. So we took an example of the Hanshin Highway network. This is data from the Hanshin Highway Express company, which manages all the highway network in Japan. They have roads with varying, some of them are very old. As you see, those red ones are 40 years old or so. And they vary in state. Some of them are mountain roads, some of them are city roads, some of them are close to coastal areas. So they vary, and also the kind of stress and pressure you see on them. The idea was, again, manual inspection costs so much time because you have to collect samples. They, for example, take them back to a lab and do a lot of mechanical engineering testing. For example, fatigue test. They apply fatigue and see, what happens. They apply light from above and see how the light disperse, which is very expensive and not reliable. People also so far have been using a little bit of camera and laser technology. This is, again, a real truck from Nexco, which manages the highway network on this side of Japan, East Japan. And this takes photos of the surface, but it doesn't tell you what's happening inside, the concrete and asphalt. So what we're looking at, again, this is a sample of mechanical inspection where they actually go around, collect this thing that looks a little bit like a burned cigarette. What you see on top is the asphalt layer, which is a very small layer. Underneath it, there's concrete. This is what you care about. Asphalt, gets wear out after some time, but the concrete is what you care about because any structural issues happen more in the concrete, and you have to decide based on the state of that whether you need to maintain the road or repave it or change it or so on, or whether it becomes a risky road or not. And there's a lot of ingenuity in mechanical engineering, and ways to test that people have been using for decades for now. There's even actually a whole test facility that should open this year in 2025, but I say robotic, which does actual scale test track. So basically, they make this road, they compose these samples, pave the road, and make trucks just go around and around and around at a very high pace to accelerate the testing, as if you can say in the amount of pressure I get in 6 months is equivalent to 10 years of actual road use, which is, again, as you imagine, is very slow, very complex, and also very expensive. So what we're thinking about is something a little different, and this is in collaboration again with Hanshin Express and SPring-8 and Oak Ridge National Lab, is to go around with a machine like this, extract samples, collect the samples. You can have a lot of samples. It depends on how frequently you sample. Is it every 10 kilometer? Is it every 1 kilometer? But you can imagine a lot of them. You send them over to RIKEN SPring-8, which is a beam source. It's a synchrotron facility, which can collect for you, 3D, projections, 2D projections, sorry, of a 3D object. And the trick is that you want to reconstruct back the image. So you need first high performance, high resolution, because the issue is to understand really what's happening inside this thing, you need high resolution. And that required many steps: collecting the specimens, scanning the specimens, and because you need high resolution, you prefer something called offset scan, where you reduce the scanning time because the cost of scanning is just so high, which means you get partial view of the data. You need first, before using any AI or anything, to do high performance image reconstruction. Those are very high resolution data, like 8K cube or 16K cube. That means you can use entire Fugaku just to reconstruct one image or a few images. But we want also to, because after you construct it, you just get basically a reconstructed 3D shape, but we don't know anything about. We want to understand more about what's the case, or what's the state of each one of those. So we need to do AI models, like the slower part, to be able to recognize and extract and segment shapes and extract data about the distribution of details and so on, so that we can actually push it more for experts, that then they can understand, for example, distribution of objects and so on. I'll not spend too much time here, but it took like some effort actually to parallelize the reconstruction of the images based on the fact that we cannot get, we have offset scans, and how to make that compute friendly and how to scale it up. Also, it's a data challenge, it's not just a compute challenge, because you are working with maybe half a petabyte of data to load, and about hundreds maybe of terabytes of data to volumes to write. So it becomes also an I/O challenge. It's not just a compute challenge. And what you get in the end is something like this. This is I think is a video. This is just showing that if this is a concrete slab, the reconstruction is giving you actually this is just going slice by slice. So this is an animated video of frame by frame in a 3D video, where you see, this is the top of the road. This is the lower part, where you see the distribution of rocks is changing. These black dots are basically air gaps, which is important because air gaps tell you if cracks might happen. The AI part was very, very actually challenging, because we cannot get label data. We cannot have experts sit down and come label this and say this is a rock, this is a rock, this is a rock, because each one of those is like 8K by 8K by 26K. So that means you have 26 slices of images in each 3D sample. That basically it becomes impossible for a human to sit down and label all of this. So we needed to find a way that you train a model that is not labeled. So that meant there should be a way, or we had to find a way. We learned the microstructure of the spread of the objects in this image, right? Graphic pipeline software, a pipeline for graphic rendering of that. So we reconstruct the object again, but in graphics, such that we can know the boundaries and we have labeled that and train with that. And then after you train the model, you want to test with real data. So this was a big challenge. And we were glad in the end when it worked. So for example, this is a real reconstructed image. And what you see on the right, it's just colored for your, for ease of understanding. And you can see that, you can find the blue parts are more bigger pebbles or rocks, and green is, more small, finer grained. And the red dots are air packets. And we were able, this resolution, to extract meaningful data. But it doesn't stop here, because once you recognize data, right, there's performance, of course, which, you have to pipeline things. You have to make sure your I/O and memory and compute is all perfectly like this overlapped. And to that, actually, we thank R-CCS to give us, a grand challenge access twice. in which we're able to scale that to full-scale Fugaku to do 46 specimens. Specimen is one of those, like, cylinder shapes that we collected. So we can do 46 of them simultaneously on the entire scale of Fugaku. And we went all the way to 16K resolution. But that's our performance part. There's the analytics part in which we don't just want to recognize like this, objects. We want to actually to do analytics such that we want to satisfy this, right? We want to, this is a list given to us by experts in Kuwait University and Hanshin Express. These are the things they need to know about the reconstructed object for them to be well informed enough to decide and make a decision, and also meet the scrutiny of the regulatory rules on that, to be able to use this method in a reliable way, right? You have to be able to measure a road shear strain angle, the density of the concrete, the distribution of voids, all this, backspaces, the volume ratio, etc., etc. But once you have this model here, which you recognize object, the rest is what we call downstream task. The rest becomes easy because then you can slice, you can find the pixel component, you can do component analysis, you can do 3D stone distribution, which means you can, hit and satisfy all this list here at a very high score. Like this is, up to 94% accuracy. And what we heard from the expert is that something around 97 or 96 should be enough for them to actually get approved regulation. So still, this is some room for improvement for us. We have to work harder, but I guess we're in the correct direction. With that, I finished, and thank you very much for listening and your time.